Ludmila. Thank you, Lisa, for the presentation. I'm a senior now in computer engineering in Brazil, but this year I've been an exchange student. During the spring semester, I was in Florida at Embry-Riddle, and now I'll be going to the Catholic University in Washington, D.C. So, the first project I worked on was with Dr. Eva Busco. It was about adding features to the Virtual Observatory's ARIS program. So, as you notice, I'm not an astronomer. I'm basically a computer engineer, so I've been programming and trying to find out and learn about astronomy on the go. So, I don't know how many of you are familiar with this ARIS spec tool. We have some points observed, the frequency, and the flux density associated with each point. This tool, SpecView, has been developed over the past 15 years by Dr. Eva Busco, and it's written in Java. So my task here was to implement some new features to make it more usable for all the astronomers. The first task that I implemented was this Boolean expression filter. So what do we see here is the metadata related to these points over here. So for each point, I know what is the error, what is the unit, what is the ID associated. And then with this filter I created, I can select things like, I want my error to be no greater than this value, or I want my data to be no older than this date. So, and then you select by the column, and then you can see the points here, and then visualize them. So here are the points selected, and then grayed out the other points. The second task was to create these segment tabs, just to make it easier to select different segments. In that first picture, I don't know if you noticed, but you had different colors, like blue, purple. These are different segments. Segments are grouped by astronomers for some common characteristics. Astronomers want to see those points as a whole, so they put them in segments. So here in this tab, you can choose to select and visualize only certain segments. Okay, the third task was to do some data coloring. Here you can select a column, and this column will be colored according to some characteristics. For example, error again. So what I did was create this scale, like the rainbow scale from red to blue, and then our error of 0 can be represented by the red color, and then the greater error is the blue. So you can visualize in a plot like this. You say, oh, okay, these points have a lot of error, and this has no error. So it's easier to evaluate how accurate are those points, or whatever you want to select them, by the date, by the unit. So here I just manipulated the values of R, G, and B to create this scale. The fourth task was about aperture correction. So Dr. Evo says, oh, I need you to correct the aperture. I was like, I'm sorry? What would be this? Could you explain? So I had a lot of lessons on astronomy. So he taught me that the aperture correction has to do with the flux of the photons arriving at the telescope. So the telescope is not capturing 100% of the light being emitted by the object. It's capturing, for example, 80%. And then if the astronomer wants to know the real flux that it's being emitted, and not only the 80%, you can use this new feature and select a new ratio. So I want to multiply the flux of all points to this value. So now I can visualize them in the plot. Like, so this point was this flux, and now I corrected it to the real flux value. Now the point is here. And you can choose to do that for points or for whole segments. So that was it for my first part. So basically all Java things with only this ARIS tool. So the second part was with Dr. Joe Polizzi, and it was about discrete event simulation testing for JWST operations. So my first part was pretty technical and Java programming hands-on. And this was basically research. So this, we still have a couple of years until the telescope is up there in the space. So this is only introductory studies. So what is discrete event simulation? Okay, oops. So how much time did you waste in line this week? That's what we are studying. We're studying queuing systems. How? So how long should JWST data take to be transmitted, received? What is it about its emergency data? What if it's an alert that has been sent, that needs to be sent to the telescope, or alert that the telescope is sending back to the Earth? We need to be able to model that to optimize these communications. Okay, the tools used. So tons of books, scientific papers, and Python. So we studied for like 1 week what would be the best language to implement these simulations. And the candidates were Python, Java, Simula. But we chose Python because of the syntax, which is really clear and direct. It's everybody, I think 90% of people here use Python. And it was fast, so the simulations would run really fast. The negative aspect is that I had to learn it from scratch. But it was fine because I'm pretty familiar with Java, but I had to admit that the Java syntax was a bit too much to say something that in Python you can say really clearly and directly. Okay, so for those who are not familiar at all with this queuing theory, what are the things that we study when we want to model a queue? What are the things that we have to think about? Oh, I don't want this client to be waiting on my queue for more than 3 minutes. What do I have to do? So things that we look are the interarrival rates, so how are customers arriving? How long they're taking to be served? How many servers I have available? Are there priority customers? And for these rates here, you can simulate by Poisson, exponential rates, Gaussian rates, or even random sometimes. When you're starting the system from scratch, sometimes say, let's just see if everybody arrives randomly, how will my system respond? So the goal here was basically to study and simulate different situations, different scenarios, and evaluate how adequate would this be for our model for the telescope. So things that we studied were the mean waiting time and the percentage of customers that got served. Because sometimes if the system is not well modeled, your line is going to grow indefinitely, and then the guy that's waiting, is the last spot, is never going to get served. That would be a horrible scenario for telescope data not being sent after spending millions to capture it. So how to avoid losing data? How to avoid that the line grows indefinitely? So next example, after studying like the taxis and the banks and things that were pretty concrete and so I had the taste of it, I started studying things that are my area, computer science engineering, which is computer architecture. So here, memory, CPU, I/O. I guess everybody's familiar. So think about a program execution. You have tasks that needs to be processed by the CPU and then sometimes sent to I/O device. For database, in a database context, I/O takes 10 times longer than CPU on average. So even if the CPU is really fast, then the process is going to get stuck here because I/O is taking 10 times longer. And that's simulating a chain of servers. And that's pretty realistic to what happens to when the telescope needs to send data. It has to go through a chain. And that can get pretty chaotic depending on the rate of the service of each part of the chain. So at first, I kind of freaked out. Because every simulation I was running, it was like, oh, the line grows indefinitely. Oh, the line, no, it's not working. The system is not processing. So, but then, relax and use SimPy. This is an amazing tool for those who love programming like I do. Here, Look, this code you can simulate the whole other drawing that I put there. Like, all this can be simulated in this 30 lines, which is pretty amazing. So here you can have simulate distribution for CPU service time, distribution for I/O service time, and then you have the commands and you have the resources. You create the entities resources, and then when a job arrives, it requests a service, and then it waits a little bit, and then it releases that resource after the job is done, which is pretty cool. So that was it for my summer. Any questions?
We gave her a little extra time since she had to do 2 projects.
Yeah.
So, questions on either project?
So what data does Iris grab? Like, is this attached to the mast services or
I don't know.
standalone?
The data is basically everything from the Hubble Telescope and from all the telescopes, all the data available. Now that it's about computer science, nobody wants to ask. I knew nobody was going to ask.
I'll wait 'cause I went there.
All right.
I'd just make the comment that there's an astrophysicist who has studied how to get people into airplanes more quickly. And so he used an astronomical data analysis technique in a simulation with various things. And then it, got him relatively his 15 seconds of fame. They actually got an investor to get a bunch of volunteers and an airplane, and they tested it. And so if you see anything in your future in this way, go for it.
No, it's true. I'm really interested in that, especially as a computer engineer for process executions inside CPUs. That's really nice for optimization. My taste.
Any other questions? All right, with that, I'll